if you need to. If you don't have any colors at home, you could just like make sure you're boxing things or make sure you underline and squiggle, but just kind of go through, start it. I don't want that option. So window, this thing. All right, so you guys should see a bigger screen. And on the bigger screen, so you're gonna see like my screen, it's not backwards. All right, so like I said, my board's not working fun. I'm also recording it for people who aren't here because we have quite a few people gone. So first thing I'm gonna do is break up my paper. And so this is kind of the goofy part. So I have my paper, I turned it sideways. So rather than the long ways, I turned it sideways. And I'm gonna draw a line not quite down the middle, but okay, so it kind of just goes throughout that whole paper. And then I'm gonna, on this side, break it apart halfway. So on my paper, I have it split close to the middle and then split halfway. If this doesn't make sense to you because you can't see my whole paper, I can do this. Oh, fun. This is what it looks like. Figuring this out, people. This was an unexpected event today when my board wasn't working. So this is how I split mine up. I tilted it, I did it the side to side. And that's just the way that I write. It makes a little bit more sense with how we're gonna do things. All right, so for our first topic, we said our first topic was exponents. So I'm gonna put all my titles in blue today. If you don't, or you could underline it, or something that makes it look more important. And remember with colors, you could use highlighters, or you could use crayons, and you go back and kind of use a crayon like color over it. I'm going to use purple for my vocabulary today. So with exponents, we just want to remember the idea of what an exponent is. If I have 5 to the third power, what does 5 to the third power mean? So you can either type in the chat or, sorry, what?
Times 5 times 5.
Perfect. 5 times 5 times 5. So it's that repeated multiplication. Okay, and this 5, we have a name specifically for the 5 and a name specifically for the 3. Does anyone remember, what do we call that bigger number, that 5?
Base.
Good, base. Base. And then, and then what do we call that? That 3 is actually the exponent. Okay, and I know it's a little blurry, but do your best to read through if you're following along. Remember, I do want you to actually write this down. So at the end of this, you're actually going to take a picture of your own piece of paper. Don't take a picture of my piece. Okay, so actually take out a piece of paper, do this with us. All right, and the other thing that I'm just gonna write for exponents just as a reminder is if I just have a number like x, how could I write that with an exponent? What exponent could I put in if it's just an x?
1.
Good. That 1 is always secretly hiding there. So I'm just going to put that in my, I don't know, that could have been an example. Now, when I do a one-pager, I have a bunch of papers I have to write. But when I had tests in college, I would make a one-pager. I didn't call it a one-pager, but I did. And I would just use examples. So mine would include like no words. I would only have examples and that's it. So this part is kind of up to you on how you would like your one-pager to look. Because I know I'm not making this just for me, I am going to include some words. But I'm going to primarily use examples. All right, so for our first one, we had like a to the 8th power times a to the 9th power. So I'm going to write all my examples in red today. And then underneath them, I'm going to write kind of like our steps in words, like how would we do this? And I'm going to put a little star there just in case you don't have, if you don't have a color, you can use that star too. So what are we going to do here? How would I simplify a to the 8th times a to the 9th? What would I do, or what would my answer?
You add the exponents.
Perfect. So I'm going to put that in my directions underneath. I'm going to add the exponents. And then in my example, I'm just going to say a to the, we're doing 8, 9. And 8 plus 9 is 17. Perfect. So that was the first type of problem that we did. And remember, for each of these problems, there's kind of a long way and then there's a short way. The long way would be if we actually wrote out a times a times a times a. We could write 8 a's there. We could write 9 a's and then count them. And together we'd have 17 a's. But the kind of the fast track is to just add those exponents. The second type of problem we dealt with had those power taken to the 7th. So that 6 is on the inside of the parentheses and the 7 is on the outside. So that means we'd have that a to the 6th. If you wanted to write it out the long way, we'd write a to the 6, a to the 6, a to the 6, a to the 6, 7 times. And so what are we going to do with those exponents this time?
Multiply.
Good. That's our fast track. We can just multiply. 6 times 7 would give us 42. And then on that first lesson, the last thing we did was very similar to this one. We had more than one thing on the inside. We had like 3, a to the 6th, b to the 4th, all taken to the 3rd power. So this one's really similar. It's really similar to this one. It's just we have more than one thing on the inside here. We have lots of things. Okay, it looks like someone's popping in and out. I can't tell if it's the same person. I can't click out of this because I got my paper here. But if you're just joining us, we're doing our one-pager, so you should take out a piece of paper. And you should follow along. All right, so what are we going to do this time?
Three times 3, 6 times 3, 4 times 3.
Good, we're going to multiply each of them by 3. So I'm going to underline that word each. Some people like to think of the word distribute. It's technically not the distributive property. And so when we look at this, we're looking at each of the inside. So in the inside, we have this 3, this a, and so Hamza had it really, really close. But we want to make sure we're multiplying each exponent by 3. So we want an exponent for this first 3. And so we need a number up here in the corner. So what is the exponent of 3? 1. So what is 3 times 1?
3.
Yep. And then 6 times 3 would be 18. And then 4 times 3 would be 12. And I just kind of accidentally wrote that up. I'm not very good at writing in straight lines. Okay, and in this case, we can simplify it. We have this 3 to that 3rd power. And so 3 to the 3rd power means we're going to do 3 times 3 times 3. So what is 3 times 3 times 3? Good, 27, yeah. So 9 times 3 is 27. So our final answer here would be 27, a to the 18th power, b to the 12th power. All right, I'm just going to kind of put a line here. I'm going to break it up just a little bit, just so I know that our second column is a little bit different than the first, but again, if you're organizing your paper differently, that's okay. So after we did these multiplication ones, where we had like multiply on the inside and we dealt with parentheses for the first time, the next thing we did was division. And we used that word quotient. So quotient meant division. And sometimes when we do that quotient, it looks like a fraction. So we'd have like x to the 12th over x to the 7th. And again, we want to write it where we only write that x one time. So how would we simplify this? How could I combine those x's? What would I do with those exponents?
Subtract.
Yeah. Remember the long way we could write 12 x's on top? We would do like x, 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 x. So if you want to do that, you pop over 7 x's, and then we would cross them out because they make ones. So when we cross them out, we're taking them away. So another way our fast track is to do that subtracting. And when we subtract, we know 12 minus 7 is 5. But a big idea that we have to do is we have to decide, is it going to go in the numerator? Is it going to go in the top? Or is it going to go on the bottom? How are we going to decide, should the x be?
Which number is the largest?
Good, yeah, good. So if we think like you could put largest here, I'm going to put more because in my brain I think of like an actual like chunk. Like there's 12 on top, there's 7 on bottom. If you want to write largest or bigger there, you could write that or whatever works for you. So here we had 12 on the top. So there is more on the top rather than the bottom. So when we subtract, 12 minus 7 is 5. In the denominator, we're left with just 1. And when we're left with that 1 on the bottom, we don't always have to write that. We can just write x to the 5th as our answer. If the 1 is in the denominator, write it. If it's in the numerator, we do have to write it. That's kind of our rules about fractions. All right, and the other we did with this multiplication, we had those parentheses, and we had like x to the 8th power over 1, and then if we took it all to the 7th. And so our rule, really, anytime we see those parentheses, what are we going to do? Close. We have a dividing here, but what are we going to do with the 7 on the outside, with those inside ones?
Distribute.
Yeah, distribute or like multiply. Remember distribute and multiplication? When you distribute, you multiply. It's similar to distribute. So we're going to multiply both the top and the bottom. And we'd get 56. On the bottom, we would do 3 times 7. And we get 21. So that was D2. And so for those of you that maybe if you wrote down your notes, it might be helpful at the top here to write like D1, D2, D3. That way, if there's not enough information on this one pager, if you have notes you can look back on, it might be helpful to label it and say, okay, if it looks like these and you need more help, go back to D2. All right, our last idea that we did was with those negative exponents. If we see we have c to the negative third power over d to the fifth power, we don't want a negative exponent in our answer. We only want positive exponents. So what are we going to do to get a positive exponent? Kind of.
Flip?
Yeah, we're going to flip. And there's still going to be that division there. Flip, and do you remember what's that word for flip when we use fractions? It starts with an R. Reciprocal. So we use that reciprocal. So that means it's going to flip or go from the top to the bottom or bottom to top or switch, whichever word you like to use. And so in this problem, I'm going to keep that fraction line there. This c to the negative third, it was in the numerator, so it's going to flip to the denominator. I'm going to put it, okay? But only that c flips because that's the only one with the negative exponent. Here we had d to the fifth, that was a positive exponent. It's going to stay just in that bottom, just like where it was. And then there's nothing left over in the top, so what number has to secretly always be hiding there?
1.
Oh. Now, if we had it where it was c to the third power, d to the negative fifth power, so pretty much the same. This time the negative was in the denominator. If it's in the bottom, it's going to flip top. So on the top, we'd still have that c to the third power, and then d to the fifth power. When it flips, it becomes a positive. So here, when that negative 3 flipped to the bottom, it becomes a positive 3 exponent. Here, when it's a negative 5 on the bottom, it flips up to the top, becomes positive. And this would be over 1. But again, like what we talked about here, when it's over, we just write that top part. Back in your brain, we only did a few examples, was when we had a 0 exponent. So if I have c to the 0 power, that means I'm going to have 0 c's there. I'm not going to write any c's. There's none. What number is always secretly hiding there, though? We didn't spend a lot of time on that because it was really quick. We see 0, we say 1. Done. So if there's anything else that you want to add to your one-pager here, add like any other words or any other examples, you could do that. I'm going to move on to the below it where we're going to write radicals. You need to see at the end, I'll kind of put my whole paper up for you guys to see if you missed anything. All right, so the second part here is going to be radicals. And again, I'm doing that in blue because that's my title. I'm also going to box it. So if you don't have colors at home, you should be using those boxes like bullet points to show, differentiate between what's what. For radicals, we have that symbol. So that's our symbol for radical. And again, in Algebra 1.2, we focused only on square roots. So I'm going to write that word square root, however you say it. And then I'm just going to jump into examples right away because I don't know what else to say about square roots. We could write out the long definition of it. So if you need to, the square root undoes repeated multiplication. But again, I'm much more of an example person, so I'm just going to show with examples what a square root is. So for my first example, I'm going to have the square root of 36.
6.
Good, 6. How did you know? Good. So I'm going to write one more vocabulary word here. I'm going to write that word perfect square. So this is what we call a perfect square because we know the square root of 36 is 6 equals 36. So that's the idea of that square root. We're trying to figure out what times itself would give us that inside amount. We didn't always work with perfect squares though. We also had unperfect squares. So we had like square root of 44. With 44, we don't have a number times itself to equal 44. So we want to simplify that. And to simplify it, we're going to break it apart into two numbers that we can multiply for. They're not going to be the same numbers. So what two numbers could we use to multiply to get to 44? What times what?
22 times 2.
We could do 22 times 2, but remember 22? We don't. So can anyone else think of another multiplication we could use to get to 44 other than 2 and 22?
4 and 11.
Yeah, and 4 and 11 I don't know what's happening. I think it's making another video. I don't know. I'm trying it out. And the reason why we want to pick 4 is because that 4 is a perfect square. So we can actually simplify that. We know the square root of 4. Square root of 4 is 2. And when we write that 2, we can take it out of that radical. We can take it out of that square. And then we don't know the square root of 11. So that's going to stay square. If we broke it up into 2 and 2, that would be fine because that multiplies to 44, but we wouldn't be able to simplify it. We don't know the square root of 2, and we don't know the square root of 22. So here we can actually simplify it that way. The other things that we simplified were I don't know. Just making a bunch of recordings. Who knows? I think I keep clicking down is the problem. All right, so when I have x to the 11th power, you guys can't see that. Now can you see it? Now can you see it? Okay, now you can kind of see it. I'm working on it. All right, so if we have the square root of x to the 11th power, how could we simplify that? What would we do?
Multiply x, like x to the, what do we call it? Okay, I forgot.
Squared?
Yeah.
Yeah. So we're going to break it up into those x squareds, and we're going to see how many would it take to get to 11. So if we have 11, we'd break it apart. This is 1, 2, 3.
5.
Yeah, 5. But if we use only 5x squareds, that would give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many x's do I need to write there?
Just x.
Yep, just x. We did need one more. So then these x squareds are going to just turn into x's because remember that square root and that squared are inverses. And we had 5 of them. So we're going to write this as x to the 5th power. And that represents that there was 5x squareds. And then we still have that square root of x. We had that one left over. So actually write it out and make x squareds. So I'm writing that kind of in the directions in my green. Another way you could do it is you could divide by 2. So if we do 11 divided by 2, how many times can 2 go into 11? 2 can fit into 11 5 times, so that's where we get this 5. And then there's 1 left over, because 5 times 2 would only be 10, so that 1 left over would go on that. So there's kind of 2 ways that you can do that. I forgot the E on this one. You can either write it out as x squareds, or you can just do that dividing by 2, whichever one makes most sense to you. All right, after we did some operations with radicals. We are getting close to done, so those of you feeling a little antsy, we're getting there, promise. Okay. And the next other, because this is going to tell me what I need to do. I need to add and subtract like radicals. I'm going to underline that word like. And what I mean by that word like is they have to be the same. Square root of 13, if I want to add something to that, it has to have that same square root. So 9 square root 13. So these ones I can combine because they have that same square root of 13. But when I combine them, what numbers will I actually add together?
The 3 and 9.
Good, the 3 and the 9. So I'm going to use the word coefficient. If you don't like the word coefficient and you want to use like outsides, or if you want to just write add 3 plus 9, you could do that. When we do adding and subtracting with radicals, we add the coefficient. So we're going to add 3 plus 9, which is 12. And then we don't add the insides because we're actually counting how many square roots of 13 there are. Here there's 3 square roots of 13. So we only add the coefficients. So that might be something you want to write there is like keep the radical or keep the inside. Radicals was multiply times 30. In this problem, what parts would we multiply? Square root. We're not quite done yet. And remember, you can use that perfect square chart. Since I'm not doing this on my computer, I can't pull that up. But there's that perfect square chart in Schoology we could use. I'm going to give you,
103.
yeah, there you go, 103. 100 times 3 is 300. And we know the square root of 100. What is the square root of 100? Good. So we have 10 square root of 3. And then our last step is this 18 does have to drop down. So we can actually multiply. I'm drawing so many arrows. Goodness. So we can actually do 18 times 10, which would be 180. So just always checking at the end to see if you can simplify. So that's everything I wrote for radicals. If you have anything else that you would like to write or it's just happening. Okay, and then we have one last section. I know we're getting close to lunch. We have about 6 minutes. We should be able to finish this section because it's pretty quick. And you guys did a really nice job with the equations. Okay, again, I'll put this up if you missed anything. I can't really tell what you can see and what you can't see because I have to cover up my screen. All right, so last section. This section I made long and narrow because with equations, when we solve, usually we solve vertically. So I'm going to as my title. If we go over on lunch, if this takes longer than 6 minutes, if you guys can just stay just for a few extra minutes and then maybe take a few extra minutes of lunch, that's okay. But if we can finish this right now, that would be really great. So for our vocabulary with equations, I'm just going to make sure I write that equal sign That way I'm remembering that I'm looking at this if I see an equal sign in that problem. Or our directions for equations is usually to solve. Our big idea with equations in this unit was if we see something taken to the second power, how would we undo something to the second power? What's the inverse?
A radical.
Yeah, the radical, the square root. Perfect. Or vice versa. If we see a square root, to undo a square root, we would take it to the second power. All right, so we have just two quick equations here. We have 4x equals 6. So I'm going to draw my line down that equal sign to help me keep things the same. And what would we undo first? Which number?
30.
Good. We see it subtracting, so we would add. And the really nice thing about inverse operations is that it allows us to write that anymore. Now we can just write that squared equals 36. And now this squared only goes with this x. If there was parentheses here and that 4 was in the parentheses, we'd have to do that squared first. But in this case, that squared only goes with the x. So at this point, we have to get rid of the 4. So how would we undo multiplying by 4?
Divide by 4.
Good. So we'd get x squared equals, what's 36 divided by 4? It's 9. And at this point, we're almost done, but not quite. We still have this squared, and our goal when we solve an equation completely by itself. So how would I undo a squared?
A radical.
Yep, the radical, that square root. So square root, square root. Square root of 9 is what times itself would give us 9?
3.
Or what other number times itself gives us 9?
-3.
This one, remember, we want two answers, and on the test I'm going to put that in the directions, or that is in the directions, reminding you you're going to have two answers. And with those two answers, remember, we have a positive and a negative. Sometimes we break that apart sooner on where that squared is. In this case, the squared, there was no parentheses, so we waited till the very end to break it apart. All right, last problem. I know we're down to like a minute, but if we can hang tight before lunch, that would be really nice. So our last one, we have 2 square root of x plus 8 equals 14. So this have a square root, and we need to undo that at some point. When we solve this, that 8 is normally what we would undo first. But this time that 8 is underneath that square root. So it's protected, we can't get to it. So we're gonna undo this 2 on the outside first. So remember, if they're touching, that means multiply. So to undo multiply, we're going to divide. Plus 8 equals 7. So at this point, we can't touch that 8 yet. It's still protected by this square root. So at this point, we have to undo the square root. So to undo the square root, we're going to take it to the second power. And if we do that on one side, we have to do it on the other side. And remember, the great thing about inverses is it undoes it. So now that we undid the square root, we can write just x plus 8. Okay. And I know it's hitting that 12-12 time, but we're like literally 1 minute away from finishing this. So 7 squared, remember, means 7 times 7. What is 7 times 7?
49.
Good, 49. So for this one, we're only going to get one answer. Because when we undo that square root, there's only one answer to 7 squared. 7 squared is only 49. And then we just have to finish it up by getting rid of that 8. Remember, the whole goal of solving is to get x by itself. And that's all I wrote for my one-pager. If you have other things that you want to add to your one-pager, you are welcome to do that. And I would use your other notes. So you should have your own piece of paper for your one-pager. You're going to take a picture of your own and submit that on Schoology. So in the week 4 folder, there is an assignment. Okay. And then